So in the last class we derived the final or we calculated the value for the total thrust under static condition. So we said that the total thrust was composed of 166 kilonewtons of thrust from the fan and 63 kilonewtons of thrust from the core engine, which worked out to 229 kilonewtons of thrust. And we compared with the this value with the value quoted by the manufacturer, which was about 233.6 kilonewtons. So the comparison appears to be reasonably good. So we come to the conclusion that the calculation procedure is probably okay. One point that you should notice is that the fan contributes to about 73% of the overall thrust, which tells you that this is a medium to high bypass ratio turbofan engine. Okay. So medium to high bypass will have numbers in the range from 75 to 80. So this tells you that it is a medium bypass ratio engine. The next thing that we wish to calculate is the mass flow rate of fuel. So let us go ahead and calculate the m dot fuel based on an energy balance for the combustor. So we did energy balance for the combustor and we showed that the mass flow rate of fuel is given by this expression m dot h times Cpg T04 minus Cp times T03 divided by the enthalpy, the calorific value of the fuel minus Cpg times T04. And if you go ahead and substitute the numbers that we had derived or that we had calculated earlier, then we get this value to be 2.64 kg per second. And as we suspected earlier, this mass flow rate of 2.64 kg per second is much less compared with the total amount of mass flow rate that goes through the engine. Remember, the air mass flow rate is around 600 kg per second or so. So this is indeed much less than that. So we were correct in neglecting m dot fuel when we add the mass flow rate of air to this. So it is indeed a small number. And if I calculate the thrust specific fuel consumption, TSFC, so TSFC is nothing but the total thrust divided by m dot fuel. In this particular problem, the combustion efficiency is not given. So the ideal value that we calculate using this formula for mass flow rate of fuel also happens to be the actual value, since combustion efficiency is not given. So T divided by m dot F comes out to be 0.0414 in units of kilogram per hour Newton is what we have calculated for this. And the manufacturer quotes a value of, so book value for TSFC is about 0.03781 kg per hour Newton. It seems to be reasonably okay for the kind of assumptions that we have made. This seems to be reasonably all right. Huh? Oh, it's the other way around. Thank you. Yes, thank you. So this is m dot F divided by T. Thank you. So the comparison seems to be all right. We are also asked to calculate, in addition to thrust and TSFC, we are also asked to calculate the area of the cold nozzle and the hot nozzle. So let us go ahead and do that. So the mass flow rate through the cold nozzle m dot C is nothing but B over B plus 1 times the total mass flow rate. And if you substitute the numbers, this comes out to be about 543.823 kg per second. And we can also use the following expression, m dot C is also going to be equal to rho E at the exit for the cold nozzle times AE C times VE C, right? M dot is also equal to rho AV, and in this expression I can write this rho as P over RT times AEC times VEC. So I know all the quantities in this expression except AEC, and I can calculate the cold nozzle area to be, if you substitute the numbers, you get the cold nozzle area to be 1.5 meter square. Remember, the cold nozzle is an annular nozzle. Okay, so this is the area of the annular nozzle, and in the same manner I can calculate the mass flow rate and the through the hot nozzle. So m dot h is going to be equal to 1 over b plus 1 times m dot. So the mass flow rate through the hot nozzle is about 126.177 kg per second, 177 kg per second, and this is also equal to rho EH times AEH times VEH, or this is nothing but PEH divided by RG times TEH. Remember, these are combustion gases, so we use R sub G here and R here for the cold air. Here this is cold air and this is combustion gases, so we use RG for this times AEH times VEH, and so this gives me AEH to be, the hot nozzle area to be 0.511 meter square. Now since the calculated value of thrust and the TSFC agree reasonably well with what the manufacturer quotes, we believe that these areas are correct. This is what the actual values are. So we have faith in these areas and we will assume that these are correct. Okay, this is important as it plays a role later on in what we are going to do. Okay. So this completes the calculation procedure for static conditions. Okay. What we will do next is calculate the same quantities for cruise at the given altitude. Right, that is what we are going to do next. We have been asked to do the same thing for cruising at an altitude of 10 kilometers. And it is given that MEA is equal to 0.8. The ambient pressure at this altitude is given to be 26.5 kilopascal, and the ambient temperature is given to be 223 Kelvin. Now we know from experience that when the engine or when the aircraft cruises at this kind of an altitude, the thrust that the engine will produce or thrust that the engine is required to produce is much less than the takeoff thrust. Remember, the static thrust or the takeoff thrust, which are almost the same, is quite high. So the same engine will produce much less thrust when it is actually cruising, right? So the throttle settings will be changed, mass flow rate of fuel will change, and other things may also change. But in the problem statement, none of these things are given. Right? We are not given, we are only given that the altitude cruises at this kind of an altitude. I am sorry, the aircraft cruises at this kind of an altitude. So we have to figure out how the conditions have to change. We will do that to some extent as we go along. For now, we will simply use the same values and go through the calculation, see if there is anything wrong with the predictions. Okay, that is our strategy now. Okay, so we start with this, and let us go through in the same manner. So I can calculate P0A to be PA times 1 plus gamma minus 1 over 2 times MA square raised to the power gamma over gamma minus 1, and if I substitute the numbers, I get this to be 40.4 kilopascal, and T0A can also be calculated in the same manner. T0A is equal to TA times 1 plus gamma minus 1 over 2 times MA square, and this comes out to be 252 Kelvin. And the free stream speed VA can be calculated as MA times square root of gamma R TA, and this comes out to be 240 meter per second. So starting from these free stream conditions, we will go through each and every state as we did before. So we go to the end of the inlet, end of the fan nozzle, which completes the fan stream. Then we will go to the compressor core stream and then finish the calculation. So at the end of the inlet or at entry to fan, since there is no energy exchange, heat or work interaction in the inlet, T01 is equal to T0A is equal to 252 Kelvin. So I need to calculate P01 also. Remember, we want T01 and P01. So I calculate P01 in the manner that we did before. So I calculate my T01S from the definition of the isentropic efficiency of the inlet. So T01S is equal to TA plus times 1 plus eta inlet plus eta inlet times T01 divided by TA minus 1. Right? This is the definition of the isentropic efficiency for the inlet. Right? So I substitute the numbers, I get my T01S to be 247 Kelvin. Once I have T01S, I can use the isentropic relationship to calculate P01S. Right? P01S is equal to PA times T01S divided by TA to the power gamma over gamma minus 1. So if I substitute the numbers, I get this to be 38.04 kilopascal, and if you remember from our earlier lecture, P01 is equal to P01S because both of them lie on the same isobar. That is how we define the efficiency. So this is equal to P01. So now I have T01 and P01. Now at the fan exit, we move to the next state. So at the fan exit, P02 is equal to P01 times fan pressure ratio, and fan pressure ratio is given to be 1.7. So which means P02 is 64.67 kilopascal. So I have P02 now, I have to calculate T02, right. Earlier I had the stagnation temperature and I needed to calculate the corresponding stagnation pressure. Now I have the stagnation pressure and I need to calculate the corresponding stagnation temperature, right, which is what we are going to do next. So remember, P02S is equal to P02. So I use that fact and do the following. Remember, P02S is equal to P01 times T02S divided by T01 raised to the power gamma over gamma minus 1, which tells me that I can calculate my T0S as T01 times P02S divided by P01 to the power gamma minus 1 over gamma, right, and P02S is equal to P02, right? Both the states lie on the same isobar, so I can substitute the numbers, and if I do that, I get T02S to be 293 Kelvin. So once I have T02s, by using the definition of the isentropic efficiency of the fan, I can calculate T02. So T02 is going to be is equal to T01 times 1 plus 1 over eta fan times T02s over T01 minus 1. So this is the definition of the isentropic efficiency of the fan, and if you substitute the numbers, I get T02 to be 296 Kelvin. So now we have P02 and T02. So the next component in the fan stream is going to be the fan nozzle. So let us go ahead and complete the fan stream. For the fan nozzle, since I know P02, I can calculate the critical pressure. PE for the cold nozzle, critical pressure is equal to P02 times 1 minus 1 over eta nozzle times gamma minus 1 over gamma plus 1 raised to the power gamma over gamma minus 1. And if you substitute the values, we get the critical pressure to be 33.43 kilopascal. And contrary to the static condition where the ambient pressure was 100 kilopascal, now the ambient pressure is 26.5 kilopascal, right, and the critical pressure is 33.43 kilopascal, which tells me that the fan nozzle is going to be choked now. In the previous case it was not choked, now fan nozzle is choked, since PA is less than PEC critical, fan nozzle is choked. So that means that the exit pressure PEC is equal to PEC critical, since the nozzle is choked, and that is equal to 33.43 kilopascal. So I know the exit static pressure, I need to calculate the exit velocity, correct? I calculate the exit velocity by making use of the fact that PEC isentropic is equal to PEC. Both of those states lie on the same isobar. So which means that I can do the following. I can use the following relationship, right? P02, let me write it like this. PEC for an isentropic process divided by P02 is equal to TEC S divided by T02 raised to the power gamma over gamma minus 1. So from this I can calculate TECS. So TECS is equal to T02 times PEC S divided by P02 raised to the power gamma minus 1 over gamma, and this value is equal to PEC. If you remember, both this and PEC lie on the same isobar. So I can substitute the value and get this temperature to be equal to 245 Kelvin. Now the actual exit static pressure TEC can be calculated from the definition of the isentropic efficiency of the nozzle in this way. So, this is equal to T0 2 minus eta nozzle times T0 2 minus T EC S. So, this gives me the actual static temperature at the exit of the coal nozzle. Substitute the numbers, we get this to be 247 Kelvin. So, I have the exit static pressure, I have the exit static temperature from which I can calculate the exit velocity, right. VEC can be calculated very easily, right. VEC is equal to, let us do that. So, VEC is equal to square root of 2 Cp times T02 minus TEC, and this comes out to be 315 meter per second. Okay. Working with these numbers also gives you an idea of what values or magnitudes these numbers have, what kind of velocities do we have at the exit of the nozzle, fan nozzle, and at the exit of the core engine nozzle, and so on. Okay. Now, the thrust from the fan stream can be written as so this is the momentum thrust plus the pressure thrust, which is nothing but so the second term is the pressure thrust. There was an area term which normally multiplies the pressure thrust. I have taken out the mass flow rate, I have divided by m dot c. So, that area divided by m dot c is what gives rise to this expression here, right. M dot c is nothing but rho EC times AEC times VEC. So, that is what I have used here to write this expression. This is the momentum thrust, this is the pressure thrust, and if you substitute the numbers, we get this to be 41.075 kilonewton plus 25.365 kilonewton, which adds up to 66.44 kilonewtons. Okay. Notice that we have not touched or changed this value of m dot. We are still assuming m dot to be whatever was given for sea level static condition. Remember, m dot was given to be 670 kg per second. We are using the same value here. Okay. And as I said earlier, it is very likely that when the engine is cruising at 10 kilometers altitude, the mass flow rate is likely to be less than what it takes in under sea level conditions. Okay. So, now the mass flow rate is less due to two reasons. Number one, the density of the air itself changes at the higher altitude, and number two, the throttle setting may also change to produce a certain amount of thrust. So, we will see what changes need to be made. For now, we will use this and then go ahead with this. Now, notice that the momentum thrust is about roughly 2 times the pressure thrust in this case. Under sea level condition, this was completely 0, only this momentum thrust was present. So, that completes the fan stream. We now move on to the core engine stream. So, as we said earlier, part of the air, an amount equal to m dot h, goes through the fan and then it goes through the core engine. So, we are going to track the m dot h amount of air which now goes through the core engine. So, we start from the fan outlet and then we go to the exit of the high pressure compressor. So, at the at the exit of the HP compressor, P03 is equal to pressure ratio PR times P01. So if you plug in the numbers, you get this to be 1156.4 kilopascal. So I know P03, I need to calculate T03 now. So what do? Same procedure as earlier. We evaluate, since I know P03, I know P03S. So I evaluate T03S, right? So T03S is equal to T02 times P03S divided by P02 raised to the power gamma minus 1 over gamma. And if I substitute the values, P03S is equal to P03, and if I substitute the values, I get this to be 675 Kelvin. Now, since I know T03S, I can use the definition of the isentropic efficiency of the turbine to calculate my T03. Right? So T03 is equal to T02 times 1 plus 1 over eta compressor times T03S divided by T02 minus 1. And if I plug in the numbers, I get this to be 708 Kelvin. So this is consistent with what we were telling earlier, that the temperature at the end of the compression process is around 700 Kelvin or so. So this confirms what we are saying earlier. So the air at the end of the compression process comes out at a temperature of around 700 Kelvin. Then we add fuel, burn fuel, to raise the temperature to some value around 1500 or 1600 Kelvin. So that is how much energy is being added in the combustor, and that is what we are going to look at next. So at the combustor exit, T04 is equal to 1500 Kelvin, and P04, it is given that there is a 5% loss of stagnation pressure in the combustor. So P04 is 0.95 times P03, and this comes out to be 1099 kilopascal. Once again, just like the total mass flow rate, we are not going to change this quantity also for now, okay? But when we are cruising at an altitude of 10 kilometers, in order to produce less thrust, the engine will take in less amount of air, plus the amount of fuel burnt will also be less, little bit less than what it is going to be for takeoff condition. But we don't know that value. We have not been given that value in the problem description. So we will proceed with this and then try to correct this or rectify this later on, okay? So let us proceed. So we will remember that this value most likely needs to be changed, and the m dot value also most likely needs to be changed. So this value also most likely needs to be changed. We will keep that in mind and proceed. So the next component is the high pressure turbine. So at the HP turbine exit, from an energy balance, remember the HP turbine produces the amount of work that is required to run the HP compressor. So T05 can be calculated based on an energy balance. So T05 is equal to T04 minus 1 over the mechanical efficiency times Cp over Cpg times T03 minus T02. And if you substitute the numbers, we get this to be 1120 Kelvin. So I have T05 now, I need to evaluate P05, right. So to do this, what I do is I calculate my T05S using the definition of the isentropic efficiency of the turbine. So I can calculate T05S is equal to T04 minus 1 over eta turbine times T04 minus T05. So this is the definition of the isentropic efficiency of the turbine. So I can calculate T05S. So if you calculate substitute the numbers, you get T05S to be 1078 Kelvin. And once I have T05S, I can actually calculate P05S using the isentropic relationship, right. So P05S is equal to P04 times T05S divided by T04 raised to the power. Now we are using gamma G, please bear that in mind, these are combustion gases. So this is gamma G over gamma G minus 1, and gamma G itself was given to be 1.333, right. So we substitute these numbers and we get P05S to be 293 kilopascal, and this is also equal to P05. So now we have both T05 and P05. The next component is the low pressure turbine. Let us go ahead and do that. So at the exit of the LP turbine, so the LP turbine produces enough power to run the fan, right. So energy balance for this gives me T06 is equal to T05 minus 1 over eta mechanical times B plus 1 times Cp over Cpg times T02 minus T01. Notice that the expression for the exit stagnation temperature of the LP turbine is a little bit different from the expression for this exit temperature for the HP turbine, mainly because there is no mass flow rate here, but there is a B plus 1 here. Mainly because the HP compressor handles an amount of air equal to m dot h. The HP turbine also handles an amount of air equal to m dot h. So that m dot cancels out. Whereas in this case, the LP turbine handles an amount of air equal to m dot h, whereas the fan handles an amount of air equal to m dot c plus m dot h, which is why we are getting this additional B plus 1 here. Okay. So you substitute the numbers and we get this to be 901 Kelvin. And once I have T06, I need to evaluate P06, and we will use the same procedure. So we calculate T06S, maybe I can write it over here. So T06S looks like this. So T06S is equal to T05 minus 1 over eta turbine times T05 minus T06. So this is the definition of the isentropic efficiency of the LP turbine, and if you substitute the numbers, you get this to be 877 Kelvin. So once I have T06S, I can calculate P06S from the isentropic relationship. So P06S is equal to P05 times T06S divided by T05 raised to the power gamma G minus 1 divided by gamma G, gamma G divided by gamma G minus 1. And this value comes out to be 110 kilopascal. So I have, now this is also equal to P06. So I have T06 and P06. The next component is the hot nozzle. So what we do is we first evaluate the critical pressure, right. So PEH for the hot nozzle, exit pressure, hot nozzle critical value is given by P06 times 1 minus 1 over eta nozzle times gamma g minus 1 divided by gamma g plus 1 raised to the power gamma g over gamma g minus 1. And if you plug in the numbers, we get this to be 58 kilopascal. And the ambient pressure is, let us see, the ambient pressure is given to be 26.5 kilopascal in this case. So since PA is less than PEH critical, hot nozzle is choked. Which means that the exit static pressure is equal to the critical pressure. Therefore, the exit static pressure PEH is equal to PEH critical, which is equal to 58 kilopascal. So I have the static pressure. Now I can calculate I have to calculate the static temperature. So what I do is I calculate TEHS, right. So TEH for isentropic process is going to be T06 times PEH isentropic process divided by P06 raised to the power gamma g minus 1 over gamma g, correct. I know PEH for the isentropic process because this is equal to PEH. Both these state points lie on the same isobar. I know this, so I can calculate TEHS, which comes out to be 767 Kelvin. Once I have this, I can evaluate TEH by using the definition of the isentropic efficiency of the nozzle, right. So TEH is equal to T06 minus eta nozzle times T06 minus TEHS. So the exit static temperature, if you substitute the numbers, comes out to be 771 Kelvin. And now I can calculate the exit velocity VEH is equal to square root of 2 times CPG times T06 minus TEH, and this comes out to be 543 meter per second. So now I can go ahead and calculate the thrust from the core engine. So T from the core engine is equal to m dot over b plus 1 times VEH minus VA, which is the momentum thrust, plus RG times TEH divided by PEH times VEH times PEH minus PA, which is the pressure thrust. And once again, I am not going to touch this mass flow rate. I will use the same value as before, and if I do that, I get this to be 38.35 kilonewton plus 28 kilonewton, which gives a total value of 66.8 0.35 kilonewton from the core engine. So, the total thrust T is equal to fan thrust plus core engine thrust, which works out to, the problem is the fan thrust, if you check back your numbers, you will see that the fan thrust was about 66 point something. So, the core engine thrust is also 66 point something. Now, they appear to be the same, okay, but the overall thrust itself reduces to about 132.79 kilonewton, okay. So, the thrust has gone down from 229 kilonewton to 132.79 kilonewton. Let us calculate the mass flow rate of fuel, and then we will compare our numbers with the book values. So, the mass flow rate of fuel m dot F can be evaluated as m dot H times CPG T04 minus Cp times T03 divided by H fuel minus CPG times T04, and if I substitute the numbers, I get this to be 2.94 kg per second. And the TSFC works out to be m dot F over total thrust works out to be about 0.08 kilogram per hour Newton. So, now we have to see whether what we are seeing at the end of the tunnel is sunlight or the headlight of an oncoming train, that we do not know yet, right. So, that we will know only when we compare these values with the actual book values. Now, the quoted value by the manufacturer for cruise thrust at this altitude is about 51.41 kilonewtons, and the TSFC that the manufacturer quotes is about 0.0642 kg per hour Newton. So, it appears that this is not light at the end of the tunnel, but the headlight of an oncoming train. So, we need to do something, right. We need to do something to make this compare better. What do we do? We can figure out what to do if we proceed in the same way as before. What if I calculate the area of the core engine nozzle and hot nozzle for these conditions? So, if I calculate the area of the cold nozzle and the hot nozzle for these conditions, I get these to be 3.661 meter square and the hot nozzle area to be 0.8855 meter square. Okay, and if you remember earlier we calculated the same values to be 1.5 meter square and this was calculated to be 0.511 meter square. So, now we can see what the problem is. We had kept m dot and T04 the same. If you do that and go ahead with the calculation, we can see that there is very poor agreement with the value quoted by the manufacturer, and the reason for that lies in this. To pass the same mass flow rate and have the same T04, we need these kinds of areas for the cold and the hot nozzle. But remember, this is a turbofan engine with fixed nozzle. It does not have adjustable area nozzles, which means that I need to redo my mass flow rate so that the nozzle area will come out to be the same. So, the same nozzle must pass that mass flow rate. So, let us start with if you start with the fan nozzle, we can simply scale down the mass flow rate, right, to agree with this. Remember our exit velocity and other things that we calculated. For example, if you look at VEH, mass flow rate was not involved in these kinds of expressions. So the VEH is not going to change. Right? VEH is not going to change. Everything was taken into account properly. Everything was a ratio. So if I scale down the mass flow rate by a factor of half, VEC will remain the same, and I should be able to get a better agreement with manufacturer quoted values. So that I can do for one nozzle. Then what do I do with the other nozzle? That is the question that we must answer next. Let us see what happens with this. So let us do this part and then we will pick it up in the next class. Okay. So we reduce the mass flow rate by a factor 3.661 meter square divided by 1.5 meter square, which gives me about 2.441, which means m dot is equal to 670 kg per second divided by 2.441. So the mass flow rate at this altitude should be 274.48 kg per second. So this directly tells me how much the mass flow rate should be changed. Okay. So now if I do this and if I recalculate my AEC for corresponding to this mass flow rate and the same VEC, VEC is not going to change. If I do that, then I will notice that AEC comes out to be 1.5 meter square. Perfect. What happens to AEH and how do we fix that is what we are going to discuss in the next class.